Now we're ready to talk about Riemann sums. In this video, I want to make sure that we cover what a left-hand Riemann sum is, as well as a right-hand Riemann sum. As we continue to talk about Riemann sums, we'll keep coming back to this particular example. So the function I'm considering is the square root of 25 minus x squared. And if you are drawing that, think about the fact that that's just the top half of a circle of radius 5. So we know that the red there would intersect at both minus 5 and positive 5. We're going to start by focusing on this value I have b. And to better help us find the value of b, I've pointed out that we can inscribe this right triangle in there. And now we can think back to some geometry. So if I need to find the value of b, we want to take advantage of the fact that we know an angle in that triangle, 45 degrees. And we also know the length of the hypotenuse because that is the radius of our circle. So we already said before, we know that that is equal to 5. So if you think about the fact that we're trying to find essentially the length of the base, then the best trig relationship to use would be cosine here. So we can notice that adjacent over hypotenuse should give me the cosine of 45 degrees. And again, thinking about that, that's going to be pi over 4. So b is 5 cosine pi over 4. And that's going to give us now 5 over the square root of 2. So that's the value of b. We'll be using that throughout. And the other thing I want to do is now focus on my region. So pull up the highlighter here. We are going to be considering the area under the curve that sits between x equals 0 and x equals b, or 5 over square root of 2. And I want to start by computing that exactly, and then we're going to try to estimate that area using Riemann sums. So to find that area, I'm going to take advantage of the fact that I could break that region into two pieces, one being the sector of the circle, and the other being that right triangle that I've found. So taking advantage of that being a right triangle. So the shaded area, I'm going to envision as being broken into two pieces. And I'm going to find the area of each of those pieces. Likely the easier one to work with is my triangle. We know that the area is 1/2 base times height. And notice that the base has length 5 over square root of 2 because we just found b. So 1/2 5 over square root of 2 squared. The sector there, what we need to think about is we can represent that area as a proportion of the total area of the circle. So this one. The total area of the circle is pi r squared, where r is 5. And what we can think about here is what is the total, we want to think what proportion the angle of that sector represents with regards to the total circle. So this angle is also going to be pi over 4 in the same way that we found that with this one. We know those add to 90 degrees or pi over 2. The entire circle should have angle 2 pi. So consequently, when we are dividing that pi over 4 by 2 pi, the ratio we're getting is 1/8. So if that angle corresponds to 1/8 of the entire angle for the circle, that area of that wedge should equal 1/8 the area of the entire circle as well. So essentially I want to add these two areas together. That's going to give me the exact area. It doesn't clean up terribly nicely, but for reference, I will tell you that you could check that this is equal to 16.0675. Again, the only reason I'm saying that is we can kind of come back in a moment and compare our estimates to that. So that's going to be the exact value of the area. And so notice we had to use some geometry. We had some shapes that were a little bit more difficult. So what I want to take a step back to is think about the best shape, which we would argue is potentially a rectangle. The reason being that to find the area of a rectangle, you simply only have to multiply length times height, and length times width. And so that's what we're going to start to look at. So our goal here in looking at Riemann sums is we want to use, or maybe I should say we want to approximate. So our goal is to approximate this area using vertical rectangles of equal width. So I'll point out that you can, in fact, define Riemann sums with rectangles of varying width. We just won't be covering that in this course. All of the Riemann sums we'll look at will have equal width for each of the rectangles. So we will use, for our illustrations here, 5 rectangles. But by the end of this lecture, we're going to talk about an arbitrary number of rectangles. So if I have 5 rectangles, one thing I want to find is that equal width that we're talking about here. So my width in this problem, coming back to our image here, the total shaded area there sits over an interval of length b, right, 0 to b, which is 5 over square root of 2. So I take that length of that interval, and I'm going to divide that by the total number of rectangles I'm using, which I've established here is going to be 5. So in doing that, we end up with our common width being 1 over square root of 2. And what I'd also like to establish here is some common notation. When we're talking about the width of these rectangles, we're going to call that delta x. The next thing, once I've established that width, I'm going to come back to an image of this region where I kind of focus on, this would be b over here. And I'll point out that each of these widths that we're looking at is equal to delta x, or 1 over square root of 2. So I've now come up with this notation of, we'll call it x sub k, to reference the edges of the rectangles along our x-axis. So we should now be able to find the value of each of those xk's as well. I'll point out there's 6 of them. So we need to find x0, we need to find x1, x2, x3, x4, and x5. The easiest values to find should always be x sub 0 and what we can more generally call x sub n, because those correspond to the endpoints of the original interval. So if you look at my graph here, x sub 0 is the leftmost edge, that's going to be 0. x5 or xn is the rightmost edge, and we already know that that's 5 over square root of 2. So I'm going to fill those in. So this is 0, and this is 5 over square root of 2. Now, to find the values in between, I take advantage of my knowledge of delta x. So the distance between x0 and x1 should be delta x. So I know that this is 1 over square root of 2. The distance between x1 and x2 should likewise be delta x. So that would make this 2 over square root of 2. And I can continue this to fill in these values. So we should always be able to exactly figure out each of these xk's, knowing delta x and the endpoints of our interval. So once I've found those, the only thing I have left to do, if you're thinking about putting these rectangles here, is I want to choose the height of those rectangles, right? They're not currently rectangles because the top is kind of curved off. We need to choose a constant height. And we have lots of choices and lots of ways in which we can do this. That's part of what we'll talk about today. To begin with, I want to illustrate what we call the left-hand sum. So once I start talking about left-hand sum, this is essentially identifying a scheme by which we'll choose the heights. So when we do this, we choose the rectangle height to be where the left edge, hence the name left-hand sum, intersects f of x. So with just that in mind, let's practice how we would draw that here, and I'll use red. So in my first rectangle, the left edge intersects f of x here. So that I'm going to choose, which of course looks identical to my curve because I'm not zoomed in. I'm going to choose that to be the height. In my second rectangle, I'm going to look for where the left edge intersects, and that's here. So I choose that to be my rectangle height. And I'm going to do this for each of the 5 rectangles, finding my new point of intersection and then leveling that off to form those rectangles. Now, when we start to talk about the left-hand sum, essentially I'm illustrating it here, and in particular, the left-hand sum is referring to the area of these rectangles that I've drawn. So once I have this, what I'm interested in is adding up the area of each of my 5 rectangles, and my goal is to use the sum of those areas as an estimate of the true area under the curve. And it's not exact because we can see that there's a mismatch, there's some corners jutting out, and this should be much easier to compute than what we did in the beginning. But of course, what's even better about this is we can look at functions where I don't have a geometric relationship that gives me the area, and so we can always fall back on this method here. So going back to my pen here, and adding up the sum, the 5 rectangle areas, a shorthand we'll use to identify that we're talking about a left-hand sum is let's not use red there. We can call it LHS. And we'll talk about in a later video that we can vary the number of rectangles. So I want to identify that I'm talking about 5 rectangles, and I can put that in my parentheses. So when we talk about left-hand sum 5 rectangles, to be clear, what that represents is the following here. My rectangles all have a common width, which I can factor out of 1 over square root of 2. And then what I want to put in parentheses then is the sum of the lengths of my rectangles. And notice that just comes back to our function f. And in particular, we want to think about what value we're plugging into f to get the heights. I know that those are my xk values, and I start with my x sub 0 value. And then in the next rectangle, we plugged in x1. And I'm going to continue this scheme. And the last rectangle used f of x4 as the height. And importantly, notice that I don't end up putting in f of x5 in there. And that's because this here does not represent the left edge of any rectangle, this line over x5. So it does not make an appearance in my left-hand sum. So if I were then to express this here, the next step would be computational. I would take these x values, plug them into our original functions, f of x equals square root of 25 minus x squared. And if you used a calculator, you would be able to get that evaluates to 16.5437. Again, usually we're not going to be working with decimals. The significance here is I can take my left-hand sum approximation and compare it to the exact value that we found above. And of course, it's not identical to that, as we should have expected looking at the picture, but it's close. So we get an idea of that. Now, just like I made this choice over here of left-hand sum, there is also a very similar scheme in which I could choose the right hand. Let's try to erase this. So I have the identical picture that I started with there, but now I'm going to look at a right, oops, that's not what I wanted to do. Please get rid of that. Okay. Right-hand sum. And just as you might expect, given what we saw with left-hand sum, the only difference, notice I kind of start with the same xk's, same delta x. The only thing that changes is my height. So now we choose where the right edge intersects f of x. Okay, so let's say blue. So in my first rectangle here, the right edge intersects f of x at this point. So I'm going to choose that to be the height. And then in the next rectangle, that would be here, and so on. And again, what we're really interested in is, once we've drawn those rectangles, what is the area that we're going to get with those? So if I were to shade these in with blue, we want to consider the area of this rectangle plus this rectangle plus this rectangle, and so on. Again, just like we saw before, I want to point out that this is not going to be exact. We see some gaps here. But the other thing I want to point out is that we should expect to get an answer different from what we got up here. We can see from the picture that those are different rectangles. But nonetheless, it would still be an estimate of what we're trying to find. So putting this back, and let me go back to the pen, I would like to identify what the right-hand sum is. So we're going to use the notation RHS to indicate right-hand sum. And I want to put in the number of rectangles again, in case later we want to identify a different number of rectangles with the same sum. The common width can once again be factored out. And just like above, I'm going to add together my heights. Now, for this one, when I look at my first rectangle, the first height was not coming from f of x0, but instead f of x1. And we see that x0 here, this is not going to give me the right edge of any of my rectangles. So consequently, that's going to be left out. So I start with f of x1, and then we have f of x2, f of x3, f of x4, and finally, f of x5. So in this scheme, we do in fact use the rightmost x value. Again, beyond this, it would be computational. I would plug these into the function that we started with, and we would be able to see that our estimate of that area is 15.508. Again, we notice just from the computation above, we get a different estimate than we did with the left-hand sum, but arguably both of these numbers are reasonable estimates of the exact area that we found earlier.